Okay, that's I am sharing a slide here. Hope all of you can see. So first example. Okay, if you see the left side is primary side, the right side is secondary side. Okay. EG means a generator 120 volt with 0 degree, the turns ratio being 5/1. The turns ratio means what? The turns ratio. Winding ratio between some textbooks they use the notation of A, some small n, but turns ratio is ratio between primary winding NP and secondary winding NS. Okay. ZL impedance of load 4 ohms and 30 degrees. So find the load voltage, the load current, generator current, power to the load, power output by the generator. Okay. Let's see. 17. Okay. First one is load voltage. Load voltage is the VL. Load voltage is VL. Okay. Load voltage here is VL. This one. Second one, load current IL. This one. Third one is generator current IG. IG is actually from this one, IG. But if you look, it goes down here to IP. So that means IG equal to IP. Primary current, P primary. Power to the load is PL. The power output by the generator, PG. Yeah. So this question is in the textbooks, so you can also read the detailed explanation in the textbooks. So the load voltage, VL, if we want to find VL, look here, VL here will be equal to ES, right? Because they are parallel. In parallel, the voltage is equal. Okay. VL will be equal to ES. We can find ES from EP. Right. We can find ES from EP. How? From the equation that ES over EP equal to NS over NP. Right? A, the turns ratio is equal to NP over NS. Okay. So that means if we want to find ES, ES will be equal to EP over A then. Okay. But then the question, what is the value of EP? If you look at the picture here, EP is parallel with EG. So the value will be the same. EP equal to EG equal to 120 volt, 0 degree. Okay. So from here we can tell 120 divided A, just now A equal to 5, right, 5. So 120 divided by 5 is 24 volt with 0 degree, because A has no degree. That is VL, IL, load current, so Ohm's law equal to VL over ZL, right? VL just now, oh, sorry, VL equal to ES then, right? So this one. Okay. So VL is 24, 0, ZL for 30 degree, right? So what is the answer? 24 divided by 4 is 6. So regarding the degree here, if it's division, so you have to subtract 0 degree minus 30 degree. Okay, it will be minus 30 degree. Ampere. The current is ampere. Okay. Third one, generator current. Generator current equal to IP. So this formula equal to ES equal AP, EP, and S equal to NP equal to IP over IS. It's in the slide. Huh? You can check the slide. So simply IP equal to IS over A, right? IS equal to IS is secondary current. Yeah. This is IS. So if you look at the drawing here, IS will be equal to IL then, because there is no resistor, capacitor, or inductor in between in parallel. So IS equal to IL. IL just now is 6, right, with minus 30 degree. So IP equal to IL over A. All right. So that means this one divided by 5. 6 divided by 5, 1.2 ampere. Degree is equal, right? D power to the load, PL. Check the formula later. Formula is there in the slide. VL, IL, cos theta. VL, we have VL. A, from A we have VL. IL, from B we have IL. The angle is 30. The angle between V and L, between V and I, which is 30. So VL is just now is 24. I is 6 cos 30. Okay. Next one is PG. PG. The formula is the same. So PG is basically VG, IG, cos. EG is 120, right? IG is equal to IP just now in C, which is 1.2. What about the degree? Is the angle between EG and IG. Between EG and IG. EG is 120 port with 0 degree. IG, which is equal to IP. IG equal to IP is minus 30 degree. Okay, so the degree is 30 degree. 120, IG is 1.2 cos 30. That's for exact first example. Okay. So basically, you just play around with the formula there. Okay, next we go to the next this one. 100 kVA, 4000 volt, 200 volt, 100 kVA is S, apparent power. 4000 is the EP, primary voltage flux. 200 is the secondary one. 50 is the frequency. And 100 secondary turns, that is NS. Okay? NS. A, primary and secondary current. Primary and secondary current. So primary IP. Primary is IP. Primary is IP is equal to S over EP. Right? S is 100,000, 100 kV, 100 kVA means 100,000. EP is 4,000. So you have 25 ampere. Right. Secondary current. secondary current is formula is equal to ES. But then S apparent power, is it the same with this one? Okay, so we assume this is ideal transformer, so the S will be equal then. Okay, the S will be equal. Unless it is stated it's not ideal transformer, so usually they will give you the apparent power for secondary part. But since there is no not mentioned, that means it is an ideal transformer. So S is 100,000, ES is 200. So this is 500 then. Right. Okay, B, number of primary turns, NP. NP. Okay, just now NP over NS equal to EP over ES, right? So NP equal to EP over ES multiplied with NS. EP is 4,000, ES is 200, NS is 100. So this one is 2,000 turn. 2,000 turns. Primary number of primary turns. C, maximum value of the flux. If we check the slide, the formula for maximum value of the flux, capital EP equal to 4.44 and P F maximum. Okay, so this is the question then. EP is 4,000. 4.44. NP is 2,000. We just have it. F is 50, so you will get the flux maximum then. Okay. Okay, yeah, that will be the second one. Let's see the third one. The third one is voltage regulation. Voltage regulation. If you read the slide, voltage regulation is transformers defined as variation of secondary voltage between no load and full load. Okay, no load and full load. But our second or third lab, fourth one, open circuit and short circuit. So 5 kVA, 200V, 400V, single phase transformer has secondary terminal voltage of 387.6 when loaded. So load here, determine regulation of the transformer. Okay, so this one, this one, EP, this is EP, this is ES. So this is step up then. This one is the condition when there is no load. No load. Okay. No load. This one is just mentioned that it's 387.6 when loaded. So determine the duration of the transformer. So according to the formula, voltage regulation, VR equal to no load voltage minus full load or load voltage, no load voltage. Okay. And remember, this is the secondary transformer. This one is on secondary terminal. So you have to use the one without load is from secondary, which is 400. Right. So 400 minus this one over 400. You will get 3.1%. 3.1%. So the variation between no load and full load, variation of secondary voltage is 3.1%. Okay. Next, okay, this one. This kind of questions is, if you look at previous exam, is always there. So maybe you can be more focused on this one. Voltage regulation, if they only give the impedance instead of the voltage itself. Okay, 100 kVA for 400 turns on primary, 80 turns on secondary. Primary, secondary impedance are given. Supply voltage 2200. Calculate equivalent impedance to primary. Voltage regulation, secondary voltage at full load when having power factor of 0.8 lagging and 0.8 leading. Okay. So just use the formula then. R equivalent. Which one? That's the R equivalent. This one. R equivalent. Use this one. This is R equivalent. And XE equivalent. Where's XE? Yeah, this one. XE equivalent. This one. Okay. But you have to be very smart that the question, it doesn't give you V. Instead, they give you turn. How many turns at primary side, how many turns at secondary side. So basically, you can manipulate the formula here, in here, equal to x1 plus x2 and 1 over n2, right? Correct? So be creative, huh? Because the question just now, they didn't give you V, they give you N instead. Same thing with this one. Same thing with this one. With R. With R here, you can rewrite the formula that RE equal to R1 plus R2 N1 N2. Okay. So what's the question just now? Okay, this one. See, they didn't give you the voltage of primary and secondary. Instead, they give you the N of primary and secondary, right? And the impedance. So if you see the solution there you are. Using N, R equivalent and X equivalent. So Z impedance is basically R plus JXE. Okay. So you get that one, and the second one asking for the voltage regulation. Okay. And the secondary voltage. And the secondary voltage at full load having power factor of 0.8 lagging and 0.8 leading. Okay. If you see here the voltage regulation and secondary voltage, this one we do for the 0.8 lagging first. So apparent power S, right? Just now is 100K. So this is 100K. 100K. This one. Okay. V1. How do you know V1? From A just now, right? From A. V1. How do you find V1? It's given in the question. Supply voltage 2200. Okay. So you get 2200 for I1 primary current. Okay. And then since cos 0.8, remember the formula? Formula is not cos, the formula is sine. Instead of cos, the formula is sine. Look here. Yeah, sine. Sine. Right? Power factor is now, the formula is cos, right? VI cos. Power factor VI cos. So power factor cos, for example, 0.8. So how do you find sine? Just use Pythagoras law. This is equal to 8 over 10, right? So cos 8 is this one, 10 is this one. This is 10. Is it? So this one, according to Pythagoras law, 100 minus 8 to the power of 2, 64. 64? Yeah, 64. 26 equal to 6. So 6 then. So sine theta equal to 6 over 10, which is 0.6. 0.6. All right. This one, 0.6. So use the formula then. Use the formula and you will get this one. This is the formula from the slide. All parameters is already you have. And then, okay, that one is for full load. That one is for full load. Yes. So secondary voltage on no load. Is it? Okay. Okay, you know this one? This is a common formula just now. You will get the V2, right? This one is given in the question. V2, and then to find the decrease of secondary voltage at full load. This one is the voltage regulation just now. So you get this one. So the value you subtract to 440. So secondary voltage as full load is this one. Okay. Remember definition of voltage regulation. Variation of secondary voltage between no load and full load. You have found the full load with voltage regulation of 3.36 full load. So no load, in no load, voltage must be less than full load, right? Okay, next is, okay, just now is lagging. Is lagging. Now is leading. What about leading? The difference, if you check the formula letter, the difference is in this one. In lagging is plus, in leading is minus. Right. So you will get this one. Okay. And this is the increase of secondary voltage. And look at this one. It's bigger. Secondary voltage is bigger at full load than the all load there, because it's leading 0.8 by 0.8. Okay. Yeah. Let's see another questions. Oh, efficiency. Okay, so efficiency of the transformer. Let me explain this one a bit. So in general, to find the efficiency, If this is input, process, this is output, input, output, efficiency is equal to efficiency is always equal to P out over P in, right? In here, sometimes that's what we call loss. So P out equal to P in minus loss over P in, right? So this one is equal to this one. This, if you look at the textbooks letter, this is the loss total. This one. Total loss. Total loss. This is the output. This is total loss. The total loss. This, if you look, this one equal to this one, right? Which is P output. P output. Same, right? If you look, let me just to make you confused. Equal to P output plus P output plus loss, right? Total loss. Because P in equal to loss, P out plus loss, or P out equal to P in minus loss. Okay. Okay, now let's see the questions. Yes, this one. 500 kVA transformer has full load copper loss of 4K watt and core iron loss of 2.5. Find kVA output through transformer efficiency is at maximum efficiency taking load factor of 0.75. Okay, if you look at the slide just now, at maximum, efficiency maximum when, show you the slide, this one. If you read this one, efficiency is maximum when variable copper loss equal to constant core or iron loss. Or in mathematical equation, this is the condition of efficiency will maximum. P means power loss of core equal to N square P copper. N is a fraction of full load. Okay. So this question, yeah. Let me show you the solution. Yeah, this one. So this is the condition of maximum efficiency. P core is given 2.5 K. P copper is also given, right? 4. So you have the fraction then, n, small n, 0.795, right, 795. So the output is to multiply n with kVA, with 500. Okay. So you have 395.5, right? Where do you get this formula? This one. It's also in the slide. If you check the slide here. Okay. Okay. Next, what's the question for? Maximum efficiency checking the load power factor PF at 0.75. 0.75. Okay. Cost. What's the power factor? So remember the maximum efficiency. Maximum efficiency is this one, the requirement. That means if you combine those two, you will have two peak core here, right? So core just now is 2.5, so you have 5. Okay, this one is given. Okay, so output power, don't forget the power factor, multiply with power factor. This one is come from the A. This one come from this one. Multiply with power factor. Input power. Input is the output plus the total loss. Output is this one. Total loss is 5. This one. You have this one. So the maximum efficiency. So just like use a common formula. 1 over losses over input power times 100%. So basically P out, right? P out over P in. P out equal to P in minus loss. P in minus loss over P in. If we divide again, P in over P in minus loss over P in, right, equal to this one, equal to this one. Yeah. P in over P in is 1. Loss over P in is this one. All right. Yeah. Okay, I think the last one. Okay, let's see the last example. Okay. This is another formula for efficiency in case they don't give you the they didn't give you the voltage or the current, right? Okay. Okay. Another formula, if they only give you, for example, S and power factor. Okay. So there are some formula for efficiency depends on the parameter given in the question. Okay. Last one. 400 kVA transformer, primary winding resistance 0.5, secondary winding resistance 0.001, iron loss 2.5 K, primary and secondary voltage 5 K and 320. So if PF of the load is 0.85, determine the efficiency on full load and on half load. On full load and half load. Okay, let's see the solution. Okay, the given at full load, find the primary current first. S is given just now 400K. S is given 400K. V also given 5K. So you have DI, primary current, AT, and P copper, loss, this is loss of a copper. The formula is that one, I1 square R1, because R1 is given 0.5. Okay, so you have loss of copper 1. Loss of copper 1 means P copper 1 means loss copper at primary side. Primary side. Okay, so don't forget, some textbook use for primary side, some textbook use P, or some another textbook use 1, another textbook use A for primary. For secondary, one textbook use 2, another textbook use S, and even another one use B for secondary. Okay, so don't get confused. So for I2, S. Why is it S the same? Because we assume the transformer is ideal. So one of the requirements that transformer is ideal, the S is the same for both primary and secondary side. Apparent power, okay, they are equal. V2, how do you get V2? V2 is given 320 volt. So from that you can find copper loss of secondary side, P copper. I2 is given, R2 is also given, right? R2 is 0.001. So you have total loss of copper from primary side combined with secondary side. P copper 1 plus P copper 2. P copper A plus P copper B. P copper primary plus P copper secondary. Okay, so P copper is the total. You add from primary and secondary, you have 4,762.5 watt total loss of copper. Okay, But then it's not the total loss yet. That one is only copper. We have iron loss here. Iron loss. Iron. This is the core loss. The loss of a material that the copper circling. The not the box. If you are imagining the shape of a transformer, right? It's like a box. The shape of the transformer, usually they shape it like a box, right? So the material, sometimes they use iron, sometimes they use steel. So even in each material, they have losses. They have loss in terms of conducting the conductivity. Okay? So in this case, it's made of iron. So the loss is it's given 2.5 K. So the total loss will be iron loss, which is the core, plus copper loss. So this one is total loss. Okay. So the output power will be apparent power multiplied with power factor. Power factor is 0.85. S is 4000 K. Okay. That one is output power. What about input power? Of course, input power equal to output plus total loss. Right. So you have this one, input power. This is output power. So the efficiency is simply, this is similar with previous formula. This is actually general formula for efficiency. You have this one. For full load, the efficiency is of transformer is 97.91. Okay. Second one is a half load. Half load. Be careful on this one. See the difference. Half load. So since the loss, especially the copper loss, is varies as the square of the current. So let me write here. So P loss of copper equal to I squared times R. Okay, both on primary and secondary side. So if it's half load, it will affect, because the one that will affect the loss here is either the R and I, right? I and I. Okay. But since it's set half load, the R is equal to, it remains the same, half. That means the new I is half then. Half is square half, power 2, to the power of 2. Okay? To the power of 2. So 1 over 4 then. 1 over 4 multiply with total copper just now in A. In A, we get total copper is this one. Okay, this one. Yes, this one. Or this one. Okay. The new total copper is this one, due to the half load. So the total loss is the iron loss plus this one. Why is it iron loss is not changing? Why? Because it has nothing to do with the load. Iron loss is the loss from the material of the transformer. It has nothing to do with the load. The load will affect only the copper loss. Okay, copper loss. So the output power, apparent power, power factor plus half load. Sorry, multiply with half load. Okay, because it is said it's half load. So you get 170 kW output. Output. So the input is this one, output plus total loss. Total loss is this one. You get from this one. Okay, so have the input power. So using this formula again, you will get, okay, this one, efficiency. This is for half load. Half load. Just now full load efficiency is 97.91. Half load 97.88. So not much different. Okay. Okay, that will be all for today. I will upload the question for our tutorial one. We will discuss that one in week 10. Now is week 8. Next week is semester break. Next week 9. Week 10, we'll have first tutorial. Thursday, and Thursday, and we'll have tests on Friday. In our class time, 3 o'clock, online test. So prepare that one. Study the quiz. I have upload how many quiz? 3 quizzes, 2 quizzes, and tutorial. I'll upload later on the tutorial. Please do the tutorial. If you can solve that one, so I'm sure you can manage to answer the test or test next 2 weeks on Friday afternoon. Okay. If you have no questions, we'll stop here. I'll see you during tutorial time next 2 weeks. Okay, thank you.
Thank you, sir. Selamat Raya.
Sama-sama.
Thank you, sir.